and IBM. Every DBMS comes with one or more accompanying database languages. The Data Definition Language, or DDL, is used by the database administrator, DBA, to define the database's logical, internal, and external schemes. These definitions will be stored in a catalog. The Data Manipulation Language, or DML, allows to retrieve, insert, delete, and modify data. DML statements can be either embedded in a general-purpose programming language or entered interactively through a front-end querying tool. SQL, or Structured Query Language, offers both DDL and DML statements for relational database systems. It can be used interactively, interactive SQL, or embedded in a programming language, embedded SQL. Database design offers various advantages, such as data and functional independence, database modeling, managing data redundancy, specifying integrity rules, concurrency control, data security, backup and recovery facilities, and performance utilities. In what follows, we will elaborate on each of these. Data independence refers to the fact that changes in data definitions have minimal to no impact on the applications using the data. These changes may occur both at the physical or logical level. More specifically, physical data independence implies that neither the applications nor the external or conceptual scheme must be changed when changes are made to the data storage specifications. For example, think about reorganizing the data across different storage locations or media, the definition of new access paths or indices, etc. The applications will keep on running successfully, maybe even faster than they did before because of the physical reorganization of the data. To successfully guarantee physical data independence, it is important that the DBMS provides interfaces between the conceptual and physical data models. Logical data independence implies that software applications are minimally impacted by changes in the conceptual or logical scheme. Think about adding new data concepts, characteristics, or relationships. The external views will act as a protective shield and mitigate the effect of these modifications on the applications. To successfully guarantee logical data independence, the DBMS must provide interfaces between the conceptual and external scheme. As we will discuss in subsequent chapters, DBMSs may also allow to store functionality, such as small routines or functions. Every function has an interface or signature containing its name together with its input and output parameters. The method or implementation then specifies how the function should be executed and is also stored in the database. Functional independence entails that changes to the function's method can be made without the applications that use it being affected. Here you can see an example of a function. Its name is calculate salary, and it has one input parameter, time worked, which represents the number of hours worked by an employee. The method then calculates the total salary, taking into account the base salary per hour and company tax. Functional independence means that the method to calculate the total salary may change without having any impact on the applications calling the function. Another key advantage of database design is the construction of a data model. Remember, a data model is an explicit representation of the data concepts together with their characteristics and relationships. It can also include integrity rules and functions. It should provide a formal and perfect mapping of the real world and is made in close collaboration with the business user. Unfortunately, as we will see later, a best case scenario with a perfect mapping is often unrealistic, and it will be important that a data model's assumptions and shortcomings are clearly documented. Popular examples of data models are the hierarchical model, the codicil model, the ER model, the relational model, and the object-oriented model. We will discuss these more extensively in subsequent chapters. Remember that one of the key drawbacks of the file approach to data management was undesired application of data, which could easily lead up to inconsistent data. In the database approach, redundant data can be successfully managed. It can be desired to duplicate data in distributed environments to improve data retrieval performance by providing local access to data rather than using resource-intensive network connections. The DBMS will now be responsible to manage the redundancy by providing synchronization facilities to safeguard data consistency. As an example, an update of a local data copy will be automatically propagated to all other data copies. Compared to the file approach, the DBMS guarantees correctness of the data. It also requires no user intervention and is thus much more efficient and less error-prone. Data integrity rules can now also be explicitly defined. These rules will allow to enforce the correctness of the data. Syntactical rules specify how the data should be represented and stored. Examples are: customer ID should be represented as a numeric value. Birth date should be stored as month, day, and year. Semantical rules focus on the semantical correctness or meaning of the data. Examples are: customer ID should be unique. Account balance should be bigger than 0. And a customer cannot be deleted if he or she has pending invoices. In the file approach, these integrity rules had to be embedded in the applications. In the database approach, they are specified as part of the conceptual scheme and stored centrally in the catalog. This substantially improves the efficiency and maintenance of the applications, since the integrity rules are now directly enforced by the DBMS whenever anything is updated.